remember what the whole point of the transformer was.
Power increase or decrease.
Power?
Voltage.
Voltage. Yes. Because power is a conserved quantity, right? So we can't really be creating or destroying it, but we can tinker with it. So we can increase the voltage and make things happen to the amperage too.
Yep.
All right? So, what type of current do transformers need supplied to them? AC. Yes. Why?
They need the alternating current to push and flow the electrons in both directions to be able to account for the voltage
I know what you mean. So it's got to be alternating because we need to create a magnetic field. And then that moving magnetic field will then create a current in another wire, right? That was the whole point. So we talked about all that. We're going to do some of those problems here at the end. So this is just how they can be built, how they can be made. So the simplest one we've already talked about. A is called an air core. That is by far the simplest one. It's just the two wires. And then we have the transfer, we have the current flowing through the first one, then it creates a magnetic field. That moving magnetic field creates a current in the secondary coil, right? This one. And ta-da! We very simple transformer. So if we fill those two coils with iron bar, then it's called open core, all right? So what does the iron bar, what does the iron bar do? What's the main reason we do that? It does, which then creates a stronger magnetic field, right? Because iron is really ferromagnetic, it's easily manipulated by magnetic fields, so it just strengthens the magnetic field in that transformer. So if we have a stronger magnetic field, then we can have a higher current flowing in that other wire. Or a stronger current, I guess. So if we go one step up, and if we connect or kind of close the loop on those iron bars, now we have part of the magnetic field that stays in here. So it's got the elephant ears, so one elephant ear is still kind of hanging out over here. The other one though is inside of this bar that's now a loop, okay? Which, again, makes it a little bit stronger. Now that it's not going outside, it's not really an external magnetic field, it's staying within that iron. Now we even have yet a stronger magnetic field that would then produce a stronger current in that other one, the second wire. Okay? Now, we can now make a shell type. So now, we're basically just having two of those boxes so that that other elephant ear has somewhere to go. Okay? It's not any longer an externalized magnetic field. So we've given it a box. So that one's going over here, that one's going over here. So even stronger magnetic field and even stronger current can be produced. Make sense? So the shell type is what's in most X-ray machines now. Write that down. So who's going to ask you that? Uh-huh. So, be able to name those and tell me which one we use the most. Okay? And I recommend Googling other pictures of them, because maybe I'll put one of these 4 pictures on the test, maybe it wouldn't. Maybe it'll be from a different book. But understand what the picture is telling you. Is it just the wires? Okay, well, if it's just the wires, it's probably the air core. Does it have the 2 bars? Open core. Are they connected? All right, are they not? Any questions about that stuff? You're like, nah.
No. No questions.
Okay. So, controlling electrical current, that's what we're still doing. So, we've talked about, briefly, how we name the transformers, right? So it was based off of how it's going to be adjusting the, yes, the voltage. So we have step up, step down, all that good stuff. So now we have this new thing called an auto transformer. This one we are using to change voltage in very small increments. We're not going to be doing very large jumps like we would with a step up or a step down transformer. So this is the first transformer, like when we're kind of traveling through the whole circuit. The auto transformer is the first of the 3 transformers that we meet. And it's called an auto transformer because there is only one coil and it operates on self-induction. So we talked about that before, how they could be self-induction or mutual induction, right? So now we have just one coil and it's wrapped around an iron core, all right, just like in the picture. There is a secondary circuit, not a secondary, I mean, it is kind of a coil, but I don't want you to really think of it that way because that's just got the taps. So what the taps do is slide up and down. So we can tell the auto transformer exactly how much adjustment in the voltage we want it to do. So this is just what's going to be transferring that voltage over, right? There has to be a connection between the two or else it would stop. So on this secondary circuit, it's going to tell the auto transformer, okay, well, I need to just adjust this up a little bit. So I'm going to knock it, like literally you can see that, how it'll tap each tap. Okay, well, I'm going to put it at 2 because I only need to increase the voltage a little bit right now. Okay? So we're not going to be using the whole coil thing, okay? Now we're talking about taps. Does that make sense? We kind of get deeper into this as we go, so that's like baseline. So for the auto transformer, we're adjusting voltage in small increments. It works on self-induction. We have one coil that's connected to another circuit to then carry on that adjusted voltage. All right? Is that okay right now? As we keep building. So there were 3 transformers in the whole X-ray circuit. So the auto transformer is the first one. Its job is to vary incoming line voltage to the appropriate level for the high voltage step-up transformer. It's gross, but we're gonna break it down a little bit. So, varies incoming line voltage. So that is straight up what's coming to the machine from the wall. What is being supplied by Evergy or KCP&L, whatever it's called now. Okay? The sucky thing about incoming line voltage is it varies. It goes up and down. They can say we're getting 220 or 110, depending on what outlet it is, but it's going to vary based off of usage in the city, based off of if there was an accident down the road that knocked over power lines, all these things. When we are creating x-rays in the tube to then shoot out to our patients, we want to know exactly what energy they have. We don't want it to be a subjective thing. We're pretty sure we're shooting 75 kV, but you never know. We cannot have that. It has to be precise. So no matter what the incoming voltage is from the power company, from the wall where it's plugged in, the auto transformer has to have an accurate flow to it. So there's this other little element, which we'll talk about later, that adjusts that so that what the auto transformer is receiving is completely accurate, and then the auto transformer can adjust it from there. Because if we send inappropriate voltage to the step-up transformer, then we are again in trouble because our energy of our X-ray beam will not be what we need it to be. If we're shooting a tow, we don't want it to have a super high voltage that's going to obliterate our picture, right? Then it would overexpose the tow, and we would have to redo it, okay? So there has to be consistency in the machine, and so the auto transformer helps us with that, okay? So we can make little adjustments in the voltage for the auto transformer before it goes to the step-up transformer, because this is the one that's giving us that mega boost from voltage to kilovoltage. Like, we work in KVs, right? But everything coming in the wall is voltage. So this makes the small adjustments so that we know it's accurate before it comes here to then go from 7 volts to 7,000. Okay? It would be more than that, but you get the point. All right? So this is the one, we're just trying to get some accuracy, make sure it's what we need. And then when it goes here, now we're going from voltage to kilovoltage for X-ray production, because we have to have super high voltage or energy, right? Voltage and energy are kind of interchangeable at this point in the tube. Does that make sense to everybody? Do I need to say any of it again? So those are those two transformers. The last one is the filament or step down transformer. So step down should tell you what's happening. Yes, we're having a decrease in voltage. So what happens when the voltage is decreased? The amperage is increased, for sure. Now, we are decreasing incoming voltage because we're trying to heat the filament in the tube. Okay? So we have to have a lot of energy, a lot of voltage for X-ray production, and we also need the filament in the tube. The filament is a little wire. We talk about it in some next chapter, or maybe, I think we do discuss it in a slide or two. So the filament is a little wire, and we need it to be outrageously hot. So if we flood that little wire with a ton of electrons, meaning a high amperage, if we flood it with a ton of electrons, that's going to increase the resistance in the wire, which then makes it really hot. Okay?
Is this the order that it goes in?
Pretty much, yeah.
You said increase resistance?
Yep.
Increase amps, okay.
Yep, if we flood that little bitty wire with a high amperage means a lot of electrons, right? So if we flood it with a lot of electrons, it increases the resistance, which makes it hot. And that is what we need. We need it to be very hot, and we need there to be a lot of electrons, and we need them to have an insane amount of voltage behind them. So all of this is getting ready for that X-ray exposure. All of this happens in like seconds. Okay? Everybody cool with that? Cool. So here's a very simple, this is just a diagram of the transformers in the tube. There's a few other things in here, and we are going to add components as we go through. So this is where it's coming in from the wall. It's our power coming in. We go to the auto transformer. We have our taps. We're going to do a little bit of adjustment in KV. And then we go to the high voltage step up transformer. What does that one do?
Increase the voltage, change the voltage from voltage.
Yes, right? We need a lot of energy now. So kind of, and it's all a big circuit. So these two things are sort of happening at the same time, okay? So part of this power, all right, we're going small adjustment, and then we're going from volts to kilovoltage with the step-up transformer. At the same time, we got some juice coming over here to the filament or step-down transformer, whose job it is to do what?
Decrease.
I think everybody's saying like a little piece of it. Everybody's right. So are we increasing or decreasing the voltage?
Increase voltage.
Because we need the amperage to be super high. Why do we need that to be super high?
Electrons, more electrons.
Yes, we need more electrons, and to get that, we have to heat it up really hot. So if these labels weren't on here, because I'm definitely going to ask you to label these, how would you know which is which?
Because of the turns.
Right. So can you elaborate?
Because a step-up transformer has more turns on the secondary side than the primary side.
Fabulous. You want to finish lecture? Because I don't. And then maybe you're like, oh crap, I don't know if this is the step up or the step down. How would you know that it's not either one of those?
Because that's taps.
Has the
It
tab.
only has one side.
Yes,
Yep.
so not every diagram will you see the dial here and the numbers,
Oh.
but they do always have this, they've got the one wire, and then they've got these little circles. So, and I'll show you, there's a few, I give you a lot of diagrams in this chapter, in this unit, because, I don't know what picture you're gonna get on the registry, you know, they have their own pictures, so you gotta be able to look at it, not just from the pictures in this one book.
Step up should always be connected to the auto transponder too, right?
Yep. And it's pretty much always gonna be laid out just about like this. The filament is always kind of at the bottom, and those are always at the top next to the tube.
So the step up will always have more on the right side, and then the step down will always have less on the right side.
Cause
Yep.
you're decreasing.
Yeah, because we have a high voltage coming in here, and we do not want a high voltage coming in this way. Because if we're decreasing the voltage, the amperage is going up. So they're named for what they're doing to the voltage. So if there's less over here, then we're stepping it down. So then it's gonna go there and do our amperage business. So there's about 2 or 3 pages in your book about capacitors. This is what I need you to know. You do get more into capacitors in your digital class, but that's like a year from now. So this is what you need to know for me right now. A capacitor is a device used to accumulate and store electric charge. It has a capacity to store, that's how I remember that, a capacity to store, it's a capacitor, right? These are typically used in mobile X-ray units where the battery usage is really high because it's running a whole lot of components, not just the tube, it's running all the electricals, charging your image receptors, all that stuff. But we need really short bursts of high voltage to expose, right? Because an X-ray tube in a mobile machine is just like the one over here. We still have to do that voltage to kilovoltage thing. And so when we're using batteries, it's got to kind of conserve its energy. That way it can still expose. So it's going to use a capacitor to store that and then be able to quickly release it in order to do that conversion from volts to kilovolts in order to expose, okay? So it's just a device to store and accumulate electrical energy or electric charge until you need it, all right? And then, you know, you'll be excited to hear about capacitors later. But for this class, that's what we need to know, okay? Any questions? Okay. So rectification. This one I do need you to know more things about. We did briefly, I don't know if I used the word rectification, but when I start blabbing about it, you're gonna be like, oh, you kind of already showed us that. Okay. So, X-ray tubes operate primarily on DC or direct current. That's what we need to happen. So auto transformers, we said, had to have AC, right? Which is handy because that's what's coming from the wall. Cool. Well, we have to do this conversion from AC to DC in order for our X-ray tube to not fail. So the electrons, as they are traveling from the cathode to the anode, have to be supplied with a direct current. It cannot be alternating anymore. That was just for transformer business. Now we have to be direct current. So, rectifiers are the devices that make this happen. They are forcing the current to flow in one direction. Okay? Rectification is just the process of changing AC to DC. So a rectifier is the device that is going to be in our circuit that makes it happen, because we have to have AC converted to DC for the X-ray tube, right? Does that make sense right now? Okay? So we had to have AC for transformers. Now we need DC for the X-ray tube. and here's why. So we have a cathode and we have an anode. The cathode's negative, the anode's positive. We are trying to take electrons and send them across. Well, they can't go backwards. And the book kind of goes into a lengthy description of why, and if you're interested, that's fine. But I'm going to tell you, if it does travel backwards, it can burn out the filament. And if you burn out the filament wire, then you have to pay lots and lots of money to get a new tube. And no one wants that. So we have these things in place to make sure that that doesn't happen. We rectify the current so that it does not end up going backwards, okay? Now, I've said filament like 80 times already, and you're like, what is that? So, it's in the cathode. It's a very thin tungsten wire, and we go deeper into the filament and all of this stuff next chapter. That's what all of next chapter is about. So this is just a teaser. The filament is a very small tungsten wire, and it's on the cathode side. We heat it very, very hot to induce thermionic emission. Thermionic emission, okay. What's thermal? What's that? You can just say electrons, it's fine. So, ionic, we're thinking electrons. So the whole point in thermionic emission is for there to be electrons just sitting and waiting. So we flood the filament with a high amperage. If it's a high amperage, there are a lot of electrons, right? Right?
Yeah.
Okay. If we have a lot of electrons, that's great. Thermionic emission is when it's so hot, it's boiling off the electrons from the wire. So you get this, your little filament wire, looks a lot like that. And so then we end up making it so bloody hot that the electrons are just hanging out. They just sit there, okay? So thermionic emission is the boiling off of electrons from a wire to create an electron cloud. There's your cloud, okay? It has been a long process to get to that point, right? You gotta have transformers, and you gotta move volts to kilovolts, and lower the voltage to increase the amperage, but that's what we are wanting to do, okay? So thermionic emission, know that term, know that the filament's made of tungsten for now, and then tomorrow we'll dive deeper into all of that, okay? So, all these electrons are negative, right? Our anode is positively charged. Well, that's handy, because opposites attract, by golly, that's great. The anode is a metal disc. We talk way more about what it's made of later. They call it a disc or a plate, just depends. Where electrons are sent for X-ray production, okay? So, what do you think the KV's job is? Where does it come in?
It's gonna help to heat up the thing,
Sorta.
to move the
Yeah, girl.
negative thing
Yeah.
toward the anode.
Thank you. Yeah, girl. So, we use the amperage to get all the electrons ready, and to get it really hot, and it's boiling it off, so then they sit here. The voltage job, because voltage is energy, right? When you apply the voltage to these electrons, then they're like, oh my god! And they go freaking out, going to the positively charged anode. So it's positive to attract the electrons. We have super high voltage pushing them along, and then there's even other stuff that we talk about next chapter that help this process. So once those electrons start hitting the anode, that's when we produce X-rays. Up until that point, it's just electrons with a lot of voltage behind them. Okay? Well, now you're like, what else do we need to know? That's how we make X-rays.
Will you explain the KVP thing again?
Yes. So, because the step-up transformer and the filament transformer, I told you those were kind of happening at the same time. So, when we have super high amperage flooding the filament wire, we're trying to get thermionic emission. all that does is boil the electrons off and make this cloud. So they just kind of sit there and hang out for a little bit. And then, at the same time, the kilovoltage that we created with the step-up transformer is then applied to this.
And that's the voltage.
Yep, the voltage and kilovoltage. So we had to
Okay.
go up to kilovoltage because we need that much power, that much energy to make these electrons go across. Okay? So then the voltage energizes all these electrons and sends them across.
To the anode.
Yeah.
Okay.
And then they start going. Okay? I sort of did that backwards. I didn't know I was going to be drawing an anode, so normally it's on the other side. Okay? Cool with that? Me too.
Yeah, only that.
Yeah.
Only this one.
The beginning, not so much.
Do I need to say anything again, or is it just like a, you need to process and absorb, and if I
Yeah.
keep talking,
Yeah.
it's gonna make it worse?
Yeah.
Yeah.
Fabulous. You can tell me these things, I'm not offended. Okay. So, we talked about why we need rectification, so now we gotta make this just a smidgen worse. This picture I don't think is from the book, but I like the simplistic, yeah, simpleness. So, we have many different varieties of rectification. Kind of. There's self and half-wave rectification. So, when this happens, half of the incoming wave, because you remember, all of our electricity, all that is a wave, right? So you still gotta, in your head, kind of picture it like that. Half of that wave is suppressed, causing one half of the current to be converted to pulsating DC. So, this is what we start out with, right? Up and down, we got major fluctuations in voltage. Sometimes it goes down to 0 and it sucks because then we got no flowage, right? So if it's half wave rectified, or self, all we're doing is getting rid of that bottom part. So the voltage is still fluctuating, just not as bad. So it's still hitting 0, and it's called pulsating because we have this pause, okay? It's not a continuous humpty hump deal like it is down here with full wave rectification. So all we did was get rid of what is below 0. There is still going to be major fluctuations all the way to 0 in the voltage, and then we have a pause in the voltage too, where it's not doing anything. And then it starts going back up, and then it goes down, and then we pause again. So that's why it's pulsating, okay? So if we have,
Is that, sorry,
Yeah.
is that DC? Would that be direct current?
it is now, so it's pulsating DC. So we're not alternating, there's no change in direction anymore, but we still have this lag in between each pulse.
And the top one is AC.
Yeah.
Okay.
Okay? So, the next best option is for full wave rectification. So this, we'll talk about numbers of rectifiers later. So full wave rectification is when now we've basically taken this bottom one and just flipped it up. So now we have direct current, right? It still fluctuates a bit. You know, we're still going down to 0, but we don't have that big lag. We don't have a pulse really anymore. Okay? It'll just keep going, but there's still major fluctuations happening. So either next chapter or the one after, we talk about how we can adjust that to drastically increase the efficiency of X-ray production. Because if you think about voltage, so you know why we have kilovoltage now, right? Because it's going to push those electrons across. So if that voltage is going up and down all the way to 0, that would mean some of those electrons are going to go, some of them aren't really going to go that well. It's not efficient, right? So if we have these electrons that had been poorly energized when they were trying to go from cathode to anode, we're gonna have a sad little low energy X-ray that's gonna be formed whenever it does hit the anode. So I kind of jumped ahead a little bit, but that's why. We don't want this to stay like this, but that's the process of getting it there. So we have several rectifiers in place, usually there's at least 4, for it to be a full wave rectification. So we would need at least 4 to make that happen, but we'll get into all of that later, okay? So does that make sense? We want the voltage to be consistent, and we're on our way there. When we start diving into more of the generators and stuff in the tube, then we'll talk about how we tinker with those waves to make it even more efficient, okay? You guys felt good, and then we talked about rectifiers, and now you're like, I get it. Any questions, though? I can say it again, or if it's just, you need to read it and read your notes and stuff, yeah.